This is your presenter, Asloob Mudassar, and I am presenting slide number 17B of the course on atomic and molecular physics. In the today's lecture, I shall be covering hyperfine interaction, hyperfine spectra in the ground state of hydrogen and sodium. And this is the second lecture of the series on hyperfine structure. And this is in continuation of the previous lecture. So to understand this lecture completely, you should consult slide number 17A first. Hyperfine structure. Consider Bj as the magnetic field which the electrons produce at the site of the nucleus. You know that in the hyperfine structure, we also talk about a field which is the field generated at the site of the nucleus due to the orbital motion of the electron. So this field, which is the Bj field, is actually different from that field. Hyperfine structure arises from the energy of the nuclear magnetic dipole moment mu I interacting with the magnetic field generated by the electron shells and the energy of the nuclear electric quadrupole moment. So you see that Bj is actually generated by the electron shells, by the presence of the electron shells, and second by the energy of the nuclear electric quadrupole moment. And the electric quadrupole moment, you know that in the atom there is a distribution of charge within the atoms. And this distribution of charge gives rise to electric field gradient. And the electric field gradient within the atom produce electric quadrupole moment, which we call as nuclear electric quadrupole moment. So the electron shells and the nuclear electric quadrupole moment together produce the field which we call as Bj, the magnetic field. So here I have given you a brief definition of the Bj, which is different from the magnetic field produced at the site of the nucleus by the orbital motion of the electron. That magnetic field is different. So now I am talking about the field Bj. Consider Bj as the magnetic field which the electron shells produce at the site of the nucleus. The magnetic field influences magnetic moment of the nucleus and orients the nuclear spin. So you see that Bj can have two purposes. That is, it can influence the magnetic moment of the nucleus and orients the nuclear spin. You know that the nuclear spin, we denote the nuclear spin by the alphabet capital I, and the nuclear magnetic moment is denoted by the symbol mu I. The result of this interaction is a coupling of the angular momenta of the electrons J and the nuclear spin I to a new total angular momentum F. You see that I have already discussed this angular momentum, total angular momentum of the electron represented by the symbol capital J in many of the previous lectures. And in the today's lecture, I am also talking about the nuclear spin capital I. So J and capital I interact together and they produce total angular momentum capital F. So in analogy with the LS coupling, we can write capital F. We are writing the vectorial equation, that is capital F is equal to capital J plus capital I. Where you see that I have explained that capital J is actually the vectorial representation of the angular momentum, total angular momentum of the electrons, and capital I is actually the vectorial form of the nuclear spin angular momentum. And capital F, you know, that is actually the total angular momentum because of capital J and capital I. And this is the vectorial representation given in equation number 18. So if you take the magnitude of the quantity F, then you see that you can write equation number 19, where on the left hand side you have the mod of f, which means that you are talking about the magnitude of the quantity f, that is the magnitude of the total angular momentum of the atom f. And on the right hand side we have the square root of f into f plus 1, and outside that one we have h bar. So this f within the square root sign is actually the total quantum number of the atom. So on the left hand side we have the magnitude of the total angular momentum of the atom, and on the left hand side we have capital F within the square root, and this capital F is actually the total quantum number of the atom. So you should clearly discriminate between the quantum number and the angular momentum. So on the left hand side we have the magnitude of the angular momentum, on the right hand side we have the square root of f into f plus 1, and that f is actually the total quantum number of the atom. You see that here we are including the effect of the nucleus also, that is the nuclear spin. So it means that we are talking about the hyperfine structure. So f can take values from 0 to plus minus 1 to plus minus 2 and so on up to plus minus j plus I. So here I have mentioned that f is equal to j plus I minus 1, and so on up to j minus I. If I is less than j, then there are two I plus 1 possibilities. And these possibilities are determined by the quantum number I. And if I is greater than j, there will be two j plus 1 possibilities. And in this case, the j will determine the value of the possibilities of the distribution of f. So I have discussed these two cases and their possibilities, that is the possibilities in which f can orient. So you see that let me discuss this figure first. On the left hand side, you know that in this figure you have total spin due to electrons represented by capital S, that is the spin angular momentum of the electrons. You have capital L as the total orbital quantum number, total orbital angular momentum of the electrons. And I have also shown their z component, that is I have shown Sz as the z component of the spin angular momentum, and I have also shown Lz as the z component of the orbital angular momentum. Here capital L is actually the total orbital angular momentum of the electrons, and here capital S is actually the total spin quantum number of the electrons. And you see that when L and S combine, it produces total angular momentum J of the atom. So I have shown J vector, I have shown S vector, I have shown L vector, and you know that I have also shown some loops over here. That is, the S vector will carry out a precessional motion about the vector J, about the total angular momentum J of the electron, and similarly the total angular momentum L of the electron will carry out a precessional motion about the total angular momentum J of the electrons. And you see that it is indicated by the precession of S is indicated by the green loop, and the precessional motion of capital L about the total angular momentum J of the electron is indicated by the red loop, and their z components are also shown. Now you see that coupling of capital S and capital L angular momenta to form the total angular momentum J of the electron. This is in the case of LS coupling. You know that in the LS coupling, L and S combine together to give you the total angular momentum J of the atom. So this is the picture which I have already discussed many times on the left hand side concerning the LS coupling and giving you the total angular momentum J of the electrons. Now on the right hand side, you can see that I have capital I as the nuclear spin, and I have capital J as the total angular momentum of the electrons. Now you see that I and J combines to give you capital F, which is the total angular momentum of the atom. And I have also shown the Z components, that is Jz, which is the Z component of a vector J, and Iz, which is the Z component of the spin angular momentum I of the nucleus. And I have also shown these two loops. So I will carry out a precessional motion in the green loops, that is the tip of the vector I will carry out a precessional motion about the vector f in the green loop, whereas J will carry out a precessional motion about the vector f following the red loop. And you see that this is the figure, this happens in case of hyperfine structure, where you take into account the nuclear spin and also the total angular momentum J of the electrons. So here in this figure, the coupling of electron angular momentum J and the nuclear angular momentum I to form the total angular momentum F of the atom. And you know that in this figure, J and I will carry out their precessional motions about the vector F. You see that I am also going to show you these two figures, in which I have in the figure on the left I have the magnetic field BL. This BL is actually the magnetic field that is produced by the orbital motion of the electron. So that's why I have capital L over here to represent that this is due to the orbital motion of the electrons. And this is produced, this is experienced at the site of the nucleus. So BL at the site of the nucleus, that is the magnetic field due to the motion of the electrons around the nucleus, will produce a magnetic field BL at the site of the nucleus. And you know that here I am also showing you mu s, where mu s is the spin magnetic moment of the electrons. Or you can also say if there are more than one electron involved, you can say that mu s is actually the total spin magnetic moment of the electrons. I have also shown the charge of the electron by E minus and the charge of the proton by E plus, separated by the distance by the vector r, and I have also shown you the velocity of the electrons with which it is moving around the nucleus. Now, let me give you a few words about this diagram, that is the calculation of spin orbit interaction. Here we have the spin orbit interaction, that is mu s interacts with PL and results in fine structure. So when mu s will interact with BL, it produces fine structure, and the fine structure is what we have discussed in many slides in some of the previous lectures. And on the figure on the right hand side, the magnetic field is represented by Bj. This magnetic field is quite different from the magnetic field BL. BL is produced by the motion of the electrons around the nucleus, whereas Bj is produced by the shell of the electrons and by the electric quadrupole moment of the nucleus. So these two produce the value of Bj at the site of the nucleus. And you know that here you have mu I. I have also shown mu I. Mu I is also located at the location of the nucleus, and mu I is the spin magnetic moment of the proton or the nucleus. And then you can see that the nucleus is represented by the charge E plus and electron by the charge E minus, whereas the electron is moving with the velocity v. And here I have shown the nuclear spin magnetic moment mu I and the Bj. Both are oriented in the same direction, because the magnetic field Bj will try to orient mu I in the direction of the magnetic field Bj. So the text relevant to this figure is calculation of hyperfine structure. Mu I, which is the spin magnetic moment of the nucleus, interacts with the magnetic field Bj due to electronic shells. So here BL on the left hand is due to the motion of the electrons around the nucleus, and Bj is actually due to the electronic shells present around the nucleus. And of course, it is also due to the electric quadrupole moment of the nucleus, but I am not going to mention those one. I shall just simply writing at that Bj is due to electronic shells. I and j precess in quantized positions around the spatially fixed vector f. The number of hyperfine levels is thus uniquely determined by the quantum numbers j and I. If j is known, I can thus be measured from the spectra. Additional magnetic potential energy due to the hyperfine interaction is. So you see that here I am going to give you the magnetic potential energy in the case of hyperfine structure shown in equation number 21, and in case of the fine structure shown in equation number 22. So let me read equation number 21. VHF, that is the magnetic potential energy in the case of hyperfine structure, is equal to minus the dot product of the spin magnetic moment mu I with the magnetic field Bj. And for the case of the fine structure, the magnetic potential energy in the case of a fine structure VFS is equal to minus times the dot product of spin magnetic moment and the magnetic field BL. So here you can see that the difference between V due to spin due to fine structure and V due to hyperfine structure. You can see that how they differ from each other. They differ in field or in the magnetic field. They also differ in the field of spin. That is, in case of hyperfine structure, we are talking about the nuclear spin, whereas in case of a fine structure, we are talking about the electronic spin. Each possible orientation of the nuclear spin I in the field Bj corresponds to a definite potential energy. So each possible orientation of the nuclear spin I in the field Bj corresponds to a definite potential energy. So let's compute this energy in much greater detail. So we have VHF is equal to minus mu I into Bj into cos of angle between mu I and Bj. That is, I have just expanded equation number 21 over here. And you can put the value of mu I, where mu I is equal to gamma times the magnitude of spin angular momentum I. So mu I has been replaced in the second step by gamma and the magnitude of vector I. And the rest of the quantities are the same. That is Bj into cos of angle between mu I and Bj. In the third step, I have substituted the value of gamma, which is gi into mu n over h bar. So the magnitude of a vector I is the same, and then the rest of the quantities are the same. And in the fourth step, I have substituted the value of I mod, which is equal to square root of I into I plus 1 multiplied by h bar. This is actually the magnitude of the vector I, which I have substituted over here and shown in red. So you see that h bar will be cancelled out, and then I am left with minus gi into mu n into the square root of I into I plus 1. Outside that one, I have a bj and cos of I and j. You see that the angle between mu I and bj is the same as the angle between I and j. So rather than mu I and mu j as the parameter of the function cos, I have simply replaced them by the vector I and j, that is cos of the angle between vector I and vector j. I and mu I are parallel, whereas j and mu j are antiparallel. You know that when we were dealing with the electronic structure of the electrons, that is the spectra of the electrons, we encountered two quantities j and mu j, and we have also noticed there that j and mu j are antiparallel to each other. Whereas for the case of nuclear parameters, these nuclear spin I and the nuclear magnetic moment mu I, they are actually parallel to each other. So from the quantum mechanical formulation, which I have also given in one of the previous, in one or more than one lectures, the angle cos of ij is equal to the magnitude, the square of f magnitude minus the square of I magnitude minus the square of j magnitude divided by 2 into magnitude of I into magnitude of j. And if you put the values of f mod square of mod of f and square of mod of I and square of mod of j, you can put their values as f into f plus 1 into h bar square plus I into I plus 1 into h bar square minus j into j plus 1 into h bar square, and h bar square will also appear in the denominator, which you can cancel out. And then the simple relationship, that is the angle of that is the cos of angle between I and j is equal to, is determined by these quantum numbers. That is the quantum number f appearing as f into f plus 1, the quantum number I appearing as I into I plus 1, the quantum number j appearing as j into j plus 1. And in the denominator, you have 2 times of square root of I into I plus 1 and the square root of j into j plus 1. So you see that we can substitute cos in equation number 23. Cos of the angle between I and j in equation number 23 can be replaced by the value of a cos of I and j from equation number 24. And in that case, you can write down the relation as given in equation number 26. So you see that this relationship that I have used over here, shown in equation number 24, and also in the previous step, these can also be inferred directly from the cosine law applied to this triangle which I have shown. That is, in this triangle I have shown the magnitude of a vector j as j into j plus 1 square root of j into j plus 1 multiplied by h bar, which is outside the square root sign, and the magnitude of I is represented by the square root of I into I plus 1, and then outside that one we have h bar, and then the square, and then the magnitude of the vector f can be represented by the square root of f into f plus 1, and outside that one we have h bar. And you know that this is what I have shown the angle. In principle, you can extend the vector j further, and then the angle is the actual angle between I and j will be actually the angle between the outgoing vector j and the outgoing vector I from the tip of the tail of both of these vectors. But you know, sir, I have shown this vector, which is the internal vector. Actually, the angle is formed at the external vector. That is the angle between I and j, where when j is extended beyond the tail of the vector I. So then the vector is formed, which we can measure easily. And so by applying the law of cosines, I have written this expression. And if you are familiar with the law of cosines, you can readily understand that how we can obtain the relationship, which is shown in equation number in this step, which is the prior first one step prior to equation number 24, where I have applied the direction law of where I have applied the law of cosines to that triangle. So you see that from this equation to equation number 24, you can expand that one and you can write the equation number 25. Or what you can do is that you can simply introduce cos of angle of I and j. This left hand side in equation number 24 can be introduced on the right hand side in equation number 23, and then the simplified result will be represented as energy of the hyperfine interaction, which is EHFS. HFS stands for the hyperfine structure, and E is the energy of a level of the hyperfine structure, which is given by A by 2. And then you have the square bracket containing F into F plus 1 minus I into I plus 1 minus J into J plus 1. This A symbol, this A constant is here called the hyperfine constant. And the value of this hyperfine constant A is equal to Gi into mu n into Dj divided by the square root of J into J plus 1. And A is a measurable quantity, also known as the interval constant. A can easily be measured from the hyperfine spectrum. So you see that equation number 26 is very important for us. We can use this equation and we can calculate the hyperfine energy of any level, provided we know the value of the quantum numbers F, I, and J. So these quantum numbers, this information, because EHF is measured from the hyperfine spectra, that is the left hand side is known, and then if the value of j is known to us, then we can find out the other values also. That is the value of I is also given to us from the nuclear physics side. We know the value of I, and from the atomic physics side we know the value of j. So we can compute the value of f in that case, and of course the hyperfine constant a is also known to us. Hyperfine splitting of a term with j is equal to 3 by 2 and I is equal to 3 by 2. So you see that here we are assuming for some case that we have the value of j is equal to 3 by 2, and in some case the nuclear spin I is equal to 3 by 2. So if we have these two values, let's construct the splitting of the hyperfine structure. So you see that on the left hand side I have represented j as a 3 by 2 and I as a 3 by 2, and then you see that I have shown this whole spectrum. You know that f is given by j, f is given by the quantum number f is given by the mod of quantum number j plus minus I. So if you sum them up, that is j plus I will give you 3 by 2 plus 3 by 2 is equal to 6 by 2 is equal to 3. So the maximum value of f will be 3. And you know that j is equal to 3 by 2 minus 3 by 2. That is j minus I, which is 3 by 2 minus 3 by 2 will be equal to 0. So f will be 0. The lowest value of f will be 0. So I need to write all those values between the maximum value and between the minimum value. The maximum value of the f was 3 and the minimum value is 0. So I am writing all the other values 3, 2, 1 and 0. So these are the possible values for the quantum number f. And you know that these levels will be 2f plus 1 times degenerate. That is, there are 2f plus 1 levels, though all these levels will have the same energy. That is, we call them as the degenerate levels. And you know that the degeneracy, that is the level of, that is the degeneracy of the level is defined by the 2f plus 1. So if f is equal to 3, then the 2f plus 1 is equal to 7. It means that this level, which is shown against the value of f is equal to 3, will actually consist of 7 degenerate levels. That is, all those levels will have the same energy, but they can be specified by different quantum numbers, but having the same energy. So these levels are referred to as the degenerate levels. So you see that the first level is represented by the value in terms of the parameters, because you can put the values of in this equation the value of f, the value of I, the value of j, because the value of I is equal to 3 by 2, the value of j is equal to 3 by 2, and the value of is what you can compute by the value of f is equal to mod of I plus minus j or j plus minus I, and through this one you can calculate different values of I, which I have explained that f will have a value of 3, 2, 1 and 0. So when the value of f is equal to 3, you can put these three values, that is the value of f is equal to 3, value of j is equal to 3 by 2, value of I is equal to 3 by 2 in the previous equation which I have shown over here, and you can find EHF in terms of the constant a to be equal to 9a over 4. So this level shown in green has a EHF value equal to, that is the EHF value, energy of the hyperfine structure corresponding to this level is plus 9a by 4. And similarly, corresponding to the quantum number f is equal to 2, shown over here, you can put the value of f is equal to 2, j is equal to 3 by 2, and I is equal to 3 by 2 in equation number 26, and you can compute the EHF energy. That is the hyperfine structure energy corresponding to this level. This level is minus 3a over 4. Similarly, the hyperfine energy corresponding to the f is equal to 1, that is to the blue level, is minus 11a over 4. And the hyperfine structure energy corresponding to f is equal to 0, that is corresponding to this red level, the lowest red level is minus 15a over 4. So you see that you can calculate delta E, which I am showing over here as the difference of energy between the two consecutive levels of the hyperfine levels. So delta E between these two consecutive levels is a 3A. That is, you can subtract these two quantities to get the value of delta E. Similarly, delta E between these this red and blue level is 2A. And the last, the delta E for the lowest possible value between these two levels is delta A is equal to A. And all these delta E are actually the hyperfine splitting energy between the two consecutive levels. And you know that these all levels are degenerate levels. Their degeneracy is given by the value given by 2f plus 1. That is, the green level on the top is 7 times the degenerate. The red level in the middle is 5 times the degenerate. The blue level, second to the bottom, is 3 times the degenerate. And the lowest red level is 1 time degenerate. So I have given you the hyperfine structure energy of these levels. I have also given you the degeneracy of these levels. Hyperfine splitting and the interval rule. Hyperfine splitting of a state with j is equal to 3 by 2 and I is equal to 3 by 2 has been explained in the figure above. Values of the quantum number f and the degree of degeneracy, which is 2f plus 1, with respect to the magnetic quantum number f, are also shown. So 2f plus 1 is actually the degeneracy. And you see that degeneracy means that these levels are actually 2f plus 1 times the degenerate. And this degeneracy of these levels will be lifted when you apply the external magnetic field to the atom. In that case, you have a quantum number which we refer to as the magnetic quantum number of the total magnetic quantum number MF. And then you see that when you have MF, and MF will appear when you apply a constant magnetic field to the atom. Actually the external magnetic field. In that case, these levels which I have shown as the singles level will split into further levels. That is, the first level will split into 7 further levels in the when we apply the external magnetic field, and then of course the magnetic quantum number MF will appear in those calculations. That is, the MF will have 7 values. The values of MF are given actually by the 2f plus 1. Bj cannot be measured independently of the magnetic properties of the nucleus itself. To find Bj from the hyperfine spectra, mu I or Gi, which are the nuclear parameters, must be known. Bj can be determined exactly for hydrogen atom as the corresponding wave functions are precisely known. You know that mu I is the spin magnetic moment of the nucleus. So from the nucleus physics side, we can know the value of mu I and of course the parameter Gi, and then of course the Bj can be determined exactly for subatoms. For example, in this case, I am mentioning the hydrogen atom because the wave functions are precisely known for the hydrogen atom. So Bj can be determined. For s electron, that is, here I am talking about the s electron of the hydrogen atom. For s electron, the electron density does not vanish at the nucleus. You can see the plots of distributions of the distribution of probabilities related with the s electron for the hydrogen atom in one of the previous lectures, and there you can see that for the s electron, the electron density does not vanish at the nucleus, and Bj can be determined. Mu I is distributed over the finite nuclear volume, and mu j interacts directly with mu I. So magnetic moment of the electrons will interact with the magnetic moment of the nucleus. So due to their interaction, the interaction is known as the contact or the Fermi interactions. And you know that this is responsible for the hyperfine structure, this interaction. For s electron of the hydrogen atom, which has a term symbol represented as 2s half. 2 is the multiplicity, half is the total quantum number of the atom or the electrons. The interaction is calculated exactly following Fermi. For the ground state of the alkali atoms, hyperfine constant A is given by. So you see that here I am just going to give you the value of the hyperfine constant A for the ground state of the alkali atoms in terms of the value of the magnitude of the wave function at r is equal to 0. So A is actually given by 2/3 into mu naught into GE into mu B into GI into mu N into the absolute square of the wave function at the origin. And you know that mu N is the nuclear magneton, mu B is the Bohr magneton, GE is actually the G factor of the electron, GI is the G factor for the nucleus, and 2/3 is the constant parameters. You know that this equation has been obtained through quantum mechanical description, which I am not going to give over here. Just I am borrowing this result from the quantum mechanics, and I am showing this result as in equation number 25, which is the value for the ground state of the alkali atoms. Psi of 0 is the value of the wave function of the electron at the nucleus. For s electron of the hydrogen atom, the value of absolute square of psi 0 is equal to 1 over pi into RH cube, where RH is the first Bohr radius. The value of A is equal to 1400. If you substitute these parameters over here, that is the value of the first Bohr radius, then you can find out the value of this constant A from equation number 25 as A is equal to 1420 megahertz, which is equal to 0.0475 centimeter inverse. And that is equal to 5.9 into 10 to the power minus 6 electron volt. For s electron in a hydrogen-like atom. So you see that here I am not talking about the hydrogen atom, but hydrogen-like atom, in which we deal only with the valence electrons. And I have also discussed at least 2 to 3 lectures on hydrogen-like atoms. So you can consult those lectures for great understanding. So for s electron in a hydrogen-like atom, the value of the absolute square of the wave function at the nucleus site is equal to z cube divided by pi into n cube into RH cube. For P, D, F, and so on, for these electrons, the probability density at the nucleus vanishes. Dj is calculated from the dipole-dipole interaction between mu j and mu I, and A becomes anisotropic. That is, the value of A may not be the same in all directions. For p electrons, Bj has value 1 order of a magnitude smaller compared with the s electron. So the value of the magnetic field Bj is reduced when we are talking about the p electron, and the reduction is 1 order of magnitude. The term diagram of the hydrogen atom, including the hyperfine structure, is shown, which is over here. This is the term diagram of the hydrogen atom for the hyperfine structure. I shall be explaining shortly this term. So first of all, let me go through the relevant paragraph. All hyperfine structure terms are doubly split by the interaction with the protons. So here we are considering that all hyperfine structures will be doubly split. So let me show you that one in the diagram. You see that these are the hyperfine structures on the rightmost side, and you know that each level is a doubly split over here. For example, at the bottom you have doubly split in black, then the red doubly split, then again green in doubly split. So these hyperfine structures are doubly split. I shall coming back to that figure for greater detail, but let me finish this paragraph first. So all hyperfine structure terms are doubly split by the interaction with the protons. The magnitude of the splitting is not to scale. In principle, these hyperfine structures are very narrow, narrower than these the spacing between P1 half and S1 half. So this splitting, that is the hyperfine structure, is actually much smaller than this splitting. But you see that I have exaggerated many times, maybe 100 times I have exaggerated the hyperfine splitting so that I can show you that this is the hyperfine splitting, but in principle this is very narrow. So the hyperfine splitting is very narrow, narrower than the fine structure splitting. And you know that this is the fine structure splitting, the splitting between S1 half, and these are, so I shall be coming back and shall explain this diagram in much greater detail. So here I am mentioning that the magnitude of the splitting for the hyperfine structure is not to scale. And I have enlarged that scale to many orders of magnitude so that you can appreciate the splitting of the hyperfine structure. The magnitude of scale is enhanced for the fine structure splitting and for the hyperfine structure splitting. So I have enhanced the splitting for the fine structure and also for the hyperfine structure. The energy splitting becomes smaller from left to right. In principle, if you move from left to right, the splitting energy should decrease. That is, from the left to right in this figure, if you move, then the splitting should decrease ultimately and becomes much smaller for the hyperfine structure splitting. But you know that we have done the reverse of that one. That is, I have exaggerated and magnified the fine structure splitting as well as the hyperfine structure splitting so that you can see the spectrum clearly and you can also appreciate their splittings. The energy splitting becomes smaller from left to right, that is from Bohr to hyperfine structure. You know that these levels n is equal to 1, n is equal to 2, n is equal to 3, and so on. These are the Bohr levels. And on the right hand side I have the hyperfine structure levels. So the energy splitting becomes smaller from left to right, that is from Bohr to hyperfine structure. The magnitude of scaling for the fine structure and especially for the hyperfine structure has been increased drastically. The splitting below the n is equal to 1 decreases and above n is equal to 1 increases. Here you can see that there is a ground state below n is equal to 1. You can see that in the ground state the hyperfine structure splitting is very small, which decreases in comparison with the hyperfine splitting gap above the n is equal to 1 level. So now the description of the paragraph is over. So let me now come back to this diagram. So on the left hand side I have the Bohr levels, Bohr model giving you n is equal to 1 level, single level, n is equal to 2 is also a single level, n is equal to 3 is also a single level due to the Bohr model. Then I have the Dirac model. You know that in the Dirac model, or you can say that this is the LS coupling model. That is the, here this is the fine structure model. And in the fine structure model, you can see that the level n is equal to is split into two levels. One level is represented by P3 half shown in green, and the other level is represented by S1 half and P1 half. Here, according to the LS interaction, that is due to the Dirac model, there is no splitting. That is, this level will appear as a single level. So we can say that n is equal to 2 level is split into two levels. One level is indicated by the two terms which are the degenerate level, which is the degenerate level having degeneracy equal to 2, and this level is S half and P half. So this level is unresolved in the Dirac model. And corresponding to n is equal to 3, I have the three levels. The first level is 2 times the degenerate having the value S half and P 1 half and S 1 half. This is unresolved level in the Dirac model. Then I have the second level shown in green. This is also a degenerate level, and the degeneracy of this level is also 2. That is, we have P3 half and D3 half levels. And then I have D5 half according to the Dirac model. And then you see that if you move further on the right hand side, you have the lamp shift. And you know that in the lamp shift, what happens is that the two levels are resolved. That is, the level which was unresolved, now it is resolved over here in the lamp shift model, which is, so you see that P1 half is the lowest level corresponding to n is equal to 2. And then the higher level is S1 half, and above that we have P3 half. So these three levels are now separated well due to the lamp shift. And then if you go further for n is equal to 3 level, you can see that the level which was unresolved having degeneracy equal to 2. So S half and P half are now split into separate levels. So P1 half is the lowest level and S1 half is the level above the P1 half level. But you see that in this figure, you see that I have not splitted the P3 half and D3 half levels. In principle, according to the lamp shift, this level should also be shifted, should also be split into two levels. Because this structure, this spectrum has been obtained with a with an instrument having limited resolution, and in that instrument this is unresolved. That is, P3 half and D3 half are unresolved in the instrument, but they are also, there is also a very small separation between them. And I have not shown that separation over here due to the scale uniformity applicable to the lamp shift splittings. Because this splitting, that is the splitting between P3 half and D3 half, is very small, unnoticeable in the lamp shift model as it is appearing over here. But in principle, there is a very small gap between these two. And of course, above that, I have D5 half. So this is the lamp shift model. And you know that above the lamp shift model, I have the hyperfine structure, hyperfine splitting. So this level, which is a single level in the lamp shift represented by 2 S1 half, will split into two levels in the hyperfine structure. And you know that I have explained this is the value of capital F, and this is the value of capital F also. The capital F is equal to 1 over here, the capital F is equal to 0 over here. Because for the hydrogen atom, the value of capital I is equal to half, and the value of capital J, which is written as a subscript with this symbol, capital J is equal to half. From this term, we can infer the value of capital J, which is equal to half, and the value of capital I for the nuclear spin for the hydrogen atom, capital I is also half. So you know that F is given by the mod of J plus minus I. So half plus half is equal to 1, and half minus half is equal to 0. So these are the two values of the the total quantum number F of the atom. So F is equal to, so with F is equal to 1, it is more energetic in comparison with F is equal to 0. So we have two splittings for the hyperfine structure. And similarly, you know that each of these P1 half level and S1 half level will split into two levels. The reason again is that the value of J for these two levels is half, and the value of the spin quantum number I is also half. So these two levels will also split into two levels. So the value of these two splitting will be f is equal to 1 and f is equal to 0. Similarly, for p1 half, the value of capital F is equal to 1 and capital F is equal to 0. Now let's consider p3 half. The value of J is equal to 3 half and the value of I for the hydrogen atom is 1 half. So 3 half plus 1 half is equal to 2 and 3 half minus 1 half is equal to 1. So the value of principal quantum number capital, so the value of the quantum total quantum number F for the state P3 half is 2 and 1, and I have separated these two levels. The separating of these two levels again is given by this equation. That is by equation number 26. So you can put the value of F, you can put the value of I and J, and you can find out the splitting between these two levels. That is the value of this can be inferred, and of course the splitting between the hyperfine levels can also be determined, which I have shown in the figure. So now let's talk about again P1 half and S1 half. For these two values, again there will be a splitting of the hyperfine structure into two levels, as I have explained for the other S half and P half values. And then you have P3 half and D3 half. These are value of J is a 3 half and value of J is a 3 half for the P3 half and D3 half. And the value of the spin, the quantum number is I is equal to 1 half. So you can combine. So P3 half will be split into two levels over here. The lower, the upper one, these two are the P3 half levels in the hyperfine structure, and the lower two in green are actually the D3 half levels in the, as seen in the hyperfine structure. And these are also, D3 is also split into two levels, and P3 half, the top one, the top green one is also split into two hyperfine structure levels. And then you have D5 half, which is again split into two levels, two hyperfine structure levels. And you know that if you go for further values, that is if you increase the value of the principal quantum number 3, then of course the splitting, the hyperfine splitting will start decreasing between the levels, and ultimately we shall reach a stage where the splitting will be almost zero. So you see that this is what I have explained, the spectrum of the hydrogen atom in its ground state, giving you the Bohr model, the Dirac model, the lamp shift model, and of course, finally, the hyperfine structure. In this case, you see that we have two lines for each hyperfine structure. It is because the value of capital I, that is the spin quantum number for the nucleus, is equal to half. I is equal to half. That's why we have only two values for each level. For atoms other than hydrogen atom, Bj and VHF, that is the magnetic potential energy of the hyperfine structure, are larger when electrons are located closer to the nucleus. So these two values are larger when the electrons are closer to the nucleus. That is for large Z, small n, and small l. For a fixed nuclear spin quantum number I, for a given type of atom, of course, the value of I will be fixed, which is the spin nuclear, which is the nuclear spin quantum number. The number of hyperfine splitting corresponding to the same are the same provided J is greater than I. So if you have J greater than I, then of course the number of splitting will be the same. And you know that here I have because you can put the value of these parameter, that is the value of a parameter I and the value of the parameter J into the formula which I have shown you before to calculate the splitting shown in equation number 26. You can calculate the energy, you can calculate the energy of each levels of the hyperfine structure, and then you can also calculate the splitting of those levels. provided you put in the value of I and j. But you know that when I is equal to 0, that is the spin quantum number is of the nucleus is 0, or the spin quantum number of the electron is 0. In either of these cases, the magnetic potential energy related with the hyperfine structure will be equal to 0. That is, there will be no hyperfine structure splitting. So when I is equal to 0 or j is equal to 0, there will be no hyperfine splitting. Magnetic field Bj, due to the outermost electrons at the nucleus, for various terms of different alkali metal atoms is shown. So you see that in this table, I am giving you the value of the Bj for different alkali metal atoms and for different states of the alkali metal atoms. For example, for the sodium, when it is in the state n is equal to 3, the term is 2s half, 2p half, and 2p3 half, and the value of the magnetic field Bj for the 2s half of the sodium is 45 Tesla. For 2p3 for 2p1 half it is 4.2 Tesla, and for 2p3 half it is 2.5 Tesla. And you can see for the higher terms the value of the magnetic field Bj will decrease, because here we are moving away from the nucleus. Similarly for the potassium, similarly for the rubidium, for the cesium, as we move away for the higher energy terms, that is move away from the nucleus, we shall find the value of the magnetic field Bj to be reduced. And these values are in Tesla, and you can compare how much reduction is carried out when you are moving from lower states to the higher states for the alkali metal atoms. If mu I is known, the magnitude of the magnetic field Bj can be determined from the measurement of the hyperfine structure, hyperfine splitting of the spectral lines. The magnetic potential energy VHF is equal to 0.027 centimeter inverse for the lowest 2s half term of the lithium, and VHF is equal to 0.3 centimeter inverse for the lowest 2s half term of the cesium. Knowing VHF, Gi and Bj, that is the product of Gi and Bj, can be calculated. The optical transition between the hyperfine structures must follow the selection rule. So if you want to, you see that in this figure, in the previous figure, that is this one, I have not shown you the transitions between these levels. Between these hyperfine structure levels, I have not shown the transitions. So if you want to show the transition between these levels, you should follow the selection rule, that is delta F should be equal to 0 plus minus 1. The relative distance between two consecutive hyperfine levels is given by, so you have delta E with the quantum numbers F plus 1 minus delta E with quantum number capital F. You subtract these two values because these two are the consecutive levels with respect to the quantum number F, then it is given by A times F plus 1. That is A times the larger value of the two quantum numbers. And you know that the two quantum numbers, I am subtracting the energy between them is F and capital and F plus 1. So the energy gap between these two will be given by equal to A times the larger of the two F numbers. If mu I, that is the spin magnetic moment, is greater than 0, the constant A, the hyperfine constant A, will also be greater than 0. Then the magnetic potential energy of the hyperfine splitting structure will increase with F. This is how the sign of mu I is determined experimentally. Even when the external magnetic field is 0, the terms are still 2F plus 1 fold degenerate with respect to MF, which is the magnetic spin quantum number. of the nucleus. Terms with the different F have different statistical weight and their intensities are proportional to 2F plus 1. So you see that when the transitions will carry out between them, then the intensities of those transitions will be proportional to the weight 2F plus 1. Now I am going to discuss the hyperfine structure in the ground state of hydrogen and sodium atoms. Proton spin I, or you can say that the nuclear spin I and the electron spin J can be oriented either parallel, giving you F is equal to 1, or anti-parallel, giving you F is equal to 0. This is what I am talking about for the hydrogen atom. Because for the hydrogen atom, we can have only two values, F is equal to 1 and F is equal to 0. The energy difference between these two configurations is delta nu bar is equal to 0.0475 centimeter inverse, or delta nu is equal to 1420 megahertz, and the corresponding wavelength is 21 centimeter. This is what I have calculated. I have given you this data for the case of the hydrogen atom. And this data, which I am producing over here, delta nu prime, delta nu, and lambda, this corresponds to the ground state of the hydrogen atom. And you know that this level represents actually the ground states of the hydrogen atom. This 1 and 0 level, the hyperfine structure level. So I am giving you the data of splitting between these two levels. That is the ground state of the hydrogen level. So this data is the data corresponding to the ground states of the hydrogen atom under the hyperfine structure splitting. The magnetic moment of the proton mu I is known to a great precision from the nuclear resonance measurement, which is the subject of nuclear physics. Delta nu bar is measured precisely. The value of G factor of the electron is found to be G is equal to 2.0023. In stellar space, the emission and absorption at a wavelength of lambda is equal to 21 centimeter due to hyperfine structure of the hydrogen atom is measurable. So you see that the spectra, the stellar spectra, corresponding to the ground states of the hydrogen atom, that is the hyperfine spectra from the stellar space of the hydrogen atom in its ground state, both in emission and absorption, can be measured to be equal to lambda is equal to 21 centimeter due to the hyperfine of the hydrogen atom. And this is measurable quantity. So now let me show you for the ground states of the hydrogen atom. So you see that this is the level and I am explaining this level. So let me show you this level in this diagram. This is the level. So now I am explaining this level in greater detail because this corresponds to the ground state of the hydrogen atom. And now I am showing you this level over here. So n is equal to 1. That is the value of the principal quantum number for the ground state of the hydrogen atom is n is equal to 1. The orbital quantum number is 0. The total quantum number G is equal to half. Because L is equal to 0 and the spin quantum number is also S half. S is equal to half spin quantum number of the electron because there is only one electron in the hydrogen atom. So if you combine L and S, you will get a total quantum number J of the electron which is equal to 1/2 in the hydrogen ground state. So if you substitute these values and if you compute, because the value of capital I, that is the spin quantum number or the nuclear quantum number of the hydrogen atom, is I is equal to 1/2 and J is also equal to 1/2. So you combine I and J to get the value of F. So if you add half plus half, you get 1. If you have half minus half, you get a 0. So you have actually two levels for the ground states of the hydrogen atom. So in this case, when you add them, that is half plus half, you have the parallel spins. If you subtract half minus half, you have the anti-parallel spins. And in this case, the total angular momentum of the atom will be F is equal to 1 in case of parallel spins and F is equal to 0 in case of anti-parallel spins. And you know that the gap between these two levels is 0.0475 centimeter inverse. And if there is a transition between these two levels, it will give you a wavelength of lambda is equal to 21 centimeter. And this dotted line represents the Bohr model, level of the Bohr model. And the level F1 exists at a height of A by 4 from the ground, from the reference level of the Bohr model, and at a level of 3 A by 4 below this reference level. Hyperfine structure of the hydrogen atom in the ground state, which is this one is the hyperfine structure of the hydrogen atom in ground state. The spins of the proton I is half and the spin of the electron J is also half, can be parallel or anti-parallel. Hyperfine splitting is 6 times smaller than the Lamb shift of the same level. So you see that you can notice, I have not mentioned graphically, but you can notice over here that the hyperfine splitting is 6 times smaller than the Lamb shift splitting of the same two levels. Now you see that next I am going to discuss. So before I finish for the case of hydrogen atom, I wanted to give one comment over here. The motion of different parts of the Milky Way galaxy relative to the Earth can be deduced from the Doppler shift of this line. The Doppler shift pattern confirmed that the Milky Way is a spiral galaxy. So you see that in the Milky Way galaxy, you have a very large number of stellar objects, and for some stellar objects you can measure the Doppler shift of this line, and then from that one you can deduce the value of the structure. You can reduce the structure of the Milky Way to be as a spiral galaxy. Now here I am giving you this structure, and this is the hyperfine splitting structure for the case of sodium. This is the sodium. So let me first of all go through the paragraph. Hyperfine splitting of the lowest terms of the sodium atom with allowed transitions and splitting spacing in megahertz. So you see that this is the hyperfine splitting of the lowest term of the sodium atom. And here again you can see that the levels are more than 2. So what is the value of the nuclear spin for the sodium atom when it is in the ground state? The value of the nuclear spin, capital I, is equal to 3 by 2. So you see that I have shown these two levels, the 3s level and the 3p level for the sodium atom. And you know that this is the transition from 2p1 half to 2s1 half, which is the D1 line of the sodium atom. And from 2p3 half to 2s1 half, this is also well known D2 line of the sodium transition. So 3s and 3p are the two well known levels in the sodium atom. And these will finally split, and fine structure splitting of these two levels is shown, which is 2s half in the ground state, and 2p1 half and 2p3 half are the fine structure splitting of the 3p level. Now let me show you the number of levels. For example, starting from the bottom, the value of J is half. From this term you can find out that the value of J is equal to 1 half. And I mentioned you that the value of the I, capital I, that is the spin quantum number capital I for the sodium atom when it is in its ground state, is 3 by 2. So half plus 3 by 2 will give you 2, and half minus 3 by 2, the mod of this one will give you 1. So I have two levels with the value of total F, that is the that is the total quantum number F is 1 and 0. and the separation which has been measured for between these two levels is 1772 megahertz. This is the splitting between these two levels. That is the level number 1 and the level number 2 in terms of the megahertz. Now let's move to the level 2p1 half. Again, the value of J is half. The value of capital I is 3 by 2 for the sodium atom in its ground state. So again, 1 half plus 3 half will give you 2. The mod of 1 half minus 3 half will give you the value of 1. So these are the two levels. And you know that the splitting between these two levels in 190 megahertz. Not the same as for the lower state, which is 1772. And you know that this scale is not, this spacing is splitting is not to scale. So the separation between the two hyperfine structures, hyperfine levels corresponding to 2p1 half is 190 megahertz. Now let's move to the level 2p3 half. The value of J is 3 half and the value of I is also 3 half. So 3 half plus 3 half will give you 3, which I have written over here. And 3 half minus 3 half will give you value of equal to 0. And you know that you have write down, you need to write down all the missing values. So you have 3, 2, 1, 0. So here 2 and 1 are the missing values which I have written. So 3 was produced when 3 half plus 3 half and 3 half minus 3 half will give you 0. So these are the values. There are 4 levels. So 2p3 half will be split into 4 hyperfine structure levels. And the splitting between these consecutive levels is given in as 59 megahertz, 34 megahertz, 16 megahertz. And the quantum number F has also been specified. And you know that I have also shown the transitions, the optical transitions among the hyperfine splitting levels, shown in 3 different colors: red, green, and light brown. For the red lines follow delta F is equal to 1. The green lines follow delta F is equal to 0. And the light brown lines follow delta F is equal to -1. So these transitions have also been shown following delta F is equal to 0 plus -1 among the hyperfine splitting levels. And you know that this splitting levels is for the sodium atom in its ground state. Hyperfine splitting of D2 lines of the sodium recorded with light from narrow band variable frequency dye laser. Hyperfine splitting of D2 lines of sodium recorded with light from a narrow band variable frequency dye laser. So you see that here I am giving you the spectra. On the left hand side you have a theoretical spectra. On the right hand side you have the experimental spectra. Both are very similar to each other. And you know that in this spectra we have delta F is equal to -1, delta F is equal to 0, and we have delta F is equal to 1. These are the 3 levels of these are the 3 transitions, and these are the peaks corresponding to these transitions. So the transitions delta F is equal to 1 give you the highest peak, and the transition following delta F is equal to 0 will give you a peak smaller than that one, and a delta F is equal to -1 give you the lowest peak. So the intensity of the peak corresponding to delta F is equal to -1 is much lower, and the peak of the intensity corresponding to delta F is equal to 0 transition is relatively better, and the peak corresponding to the transition giving you delta F is equal to 1 is much better, is much enhanced. So similarly, you can measure the experimental data, which is given on the right hand side of that one. And I have also shown the scale of this level is indicated by 20 megahertz arrow. This arrow indicates that what is the scale over here in terms of a megahertz. And this is the spectrum corresponding to the D2 lines. You know that when you have the D2 lines, the D2 lines is actually the transition from 2p3 half to the ground state, which is 2s half. So if you carry out the transition from the D2, you know that how many levels corresponding to 2p3 half is 1, 2, 3, 4 levels. These are the 4 hyperfine structure levels corresponding to 2p3 half, and the level and the fine structure level corresponding to 2s half are only the 2 levels. So you see that the transitions which will follow to the ground state of this level, these are the 3 lines as indicated by the first 3 lines. So these first 3 lines, the spectra corresponding to first 3 lines in theoretically is given on the left hand side, and the experimentally measured data for the transitions which I have mentioned, that is from the f is equal to 2, 1 and 0 transitional levels of the hyperfine levels corresponding to 2p3 half to the ground state level, which is 2s1 half, which is this level, has been shown experimentally and theoretically. Delta f for the ground state and for the excited states are given. The curve on the left hand side is calculated from the natural line width, and the curve on the right hand side is the experimentally measured data. So you see that the natural line width has been used in order to predict the width of these peaks. Natural line width has been used, and this is the experimental data in which the line width is slightly greater than the line width of the spectra shown on the left. The curve on the right is an experimentally measured data. Hyperfine splitting of the level of the 3 levels. You know that here the 3 levels of the sodium, I have shown you in this diagram that this is the splitting, hyperfine splitting of the 3 levels of the levels of the sodium, which give you three levels, 2ps half, 2p 1 half and 2p3 half. Corresponding to these 3 levels, the splitting hyperfine splittings have been shown. So hyperfine splitting of the 3 levels, and these levels were 2p 2s1 half, 2p 1 half, 2p3 half of the sodium, and for 2s1 half and 2p1 half, the value of capital I is equal to 3 by 2 and capital J is equal to half. Capital J is equal to half for S1 half and P1 half. So if you combine together, you will get capital F is equal to 2 and 1. And for the third term, which is 2p3 half, the value of J is 3 half. The value of I is the same for the sodium atom in its ground state, which is I is equal to 3 half. So if you combine these 2 half, that is I is equal to 3 half and J is equal to 3 half, you will get these values of F to be equal to 3210. Optical transitions with the selection rule delta F is equal to 0 plus minus 1 are shown in the previous figure. Due to finite line width, only 2 components of D1 with the delta 1 is equal to 0.023 angstrom and 2 components of D2 with the delta is equal to 0.021 angstrom are observed. So you see that for the transitions for corresponding to the D2 line, you know that a D2 line is the line in which the transition from 2p3 half takes place to the ground level, which is 2s half. So their corresponding hyperfine structure levels are 4 in number, and their transition to the ground state will actually produce 2 levels with a significant amount of intensity. And similarly, for the transition from the hyperfine splittings, hyperfine levels corresponding to 2p1 half, which is the level for the D1 level, will also produce 2 levels with a significant intensity, because the third level will not produce enough intensity to be recorded. The then recorded spectrum, that is the spectrum which was recorded for the first time with the highest available resolution, was obtained by exciting resonance fluorescence in a beam of sodium atom. That is exciting, that is the resonance fluorescence was excited in the sodium atom to observe these lines with a very narrow band variable frequency dye lasers. So you see that this is what I have explained. Details about further details in the lecture. This is lecture number 2, where I have covered some more details about the hyperfine structures. I have given you the interactions between hyperfine structures, how these levels are produced, what are their graphical representations, what is the value of capital J and how it differs from the value of capital from the what is the value of Bj and how it differs from the value of Bl. Their splitting energies have also been given. And then on the basis of these splitting energies, I have calculated the spectrum of the hydrogen atom. And with much detail, I have borrowed something from quantum mechanics, giving you the values of the value of some unknown parameters. And then of course, I have given you the value of the hydrogen atom and their corresponding hyperfine structural splittings for the levels corresponding to n is equal to 1, n is equal to 2, and n is equal to 3. The hyperfine structural splittings have been given. And also I have given you the comparison between Bohr model, Dirac model, Lamp-shift model, and the hyperfine structure models. Their values of the Bj for different alkali metal atoms in their different states has also been given. And then of course the ground states of the hydrogen atom and the sodium atom have been very well explained in this lecture. This is for the sodium, for the hydrogen atom, and this is for the sodium. And these are the measurement corresponding to D1 and D2 lines in theoretical and experimental data. And you see that this lecture is continued. And this is the end of lecture number 2 of the course on hyperfine structuring.